steel, the quintessential material of modern civilization, stands as a testament to human ingenuity and the marvels of engineering and physics interwoven in its creation. Let us embark on a journey through the labyrinth of metallurgy, exploring the intricate dance of atoms and the mighty forces that shape steel into the backbone of our industrial world. At its core, steel is an alloy, a fusion of iron and carbon, with small amounts of other elements added to enhance its properties. This seemingly simple composition belies the complexity of its production and the profound implications it holds for myriad applications. The journey of steel begins in the fiery depths of a blast furnace, where iron ore, limestone, and coke, a derivative of coal, converge in a crucible of intense heat. Here, the alchemy of metallurgy unfolds as temperatures soar to over 1,500 degrees Celsius, melting the iron ore and reducing it to its elemental form. The limestone acts as a flux, binding impurities and allowing them to be skimmed off, while the coke provides the necessary carbon for the alloy. As the molten iron is drawn from the furnace, it undergoes a transformation akin to a symphony of physics, through a process known as basimerization or basic oxygen steelmaking. Impurities such as sulfur, phosphorus, and excess carbon are further purged, leaving behind a molten pool of refined iron, known as hot metal. This molten metal is then carefully alloyed with precise amounts of carbon, typically between 0.2% to 2.1%, depending on the desired properties of the steel. But steel's journey does not end here. It is merely the beginning of a meticulous orchestration of heat treatment, shaping, and manipulation. Through processes like quenching and tempering, the molecular structure of steel is fine-tuned, imparting strength, toughness, and resilience. Imagine the atoms within the steel lattice, dancing to the tune of heat, aligning themselves into intricate patterns that dictate the material's mechanical properties. The physics behind steel's strength lies in its crystalline structure. At the atomic level, iron atoms arrange themselves in a cubic lattice, forming grains that give steel its distinct texture. The alignment of these grains, coupled with the presence of carbon atoms interspersed within, creates barriers that impede the movement of dislocations or tiny defects in the lattice, thereby reinforcing the material against deformation. Moreover, the addition of alloying elements such as manganese, chromium, nickel, and molybdenum introduces further complexity to the steel matrix, enhancing its corrosion resistance, hardness, and machinability. Each element plays a distinct role in the interplay of forces within the steel, influencing its behavior under varying conditions of stress, temperature, and environment. Indeed, the engineering prowess encapsulated within the realm of steel knows no bounds, from the towering skyscrapers that pierce the heavens to the humble bridges that span yawning chasms. Steel stands as a testament to human achievement and the triumph of intellect over adversity. Its versatility knows no bounds, finding application in industries as diverse as automotive, aerospace, construction, and manufacturing. In the crucible of innovation, steel continues to evolve, spurred onward by the relentless quest for perfection. Advanced techniques such as microalloying, powder metallurgy, and thermomechanical processing push the boundaries of what is possible, ushering in a new era of high-performance materials with unparalleled strength-to-weight ratios and unprecedented durability. The engineering and physics behind steel are a tapestry woven from the fabric of human endeavor, a testament to the boundless potential of scientific inquiry and technological innovation. As we stand on the precipice of a new age, let us marvel at the wonders of steel and the infinite possibilities it holds for the future of humanity. At its core, steel embodies the elegant fusion of iron and carbon, two elemental titans whose union transcends mere chemistry to shape the very fabric of our modern world. This marriage of elements, seemingly straightforward in its composition, belies the intricate dance of atoms and the symphony of physics orchestrating its creation. Within the crucible of a blast furnace, where temperatures soar to searing heights, iron ore undergoes a metamorphosis, shedding impurities and embracing carbon's embrace, giving birth to the molten essence of steel. Yet, this transformation is not merely a chemical reaction but a ballet of thermodynamics, where heat and pressure conspire to mold raw materials into a substance of unparalleled strength and resilience. As the molten metal emerges from the fiery depths of the furnace, it enters a realm where engineering meets alchemy, where the laws of physics reign supreme. Through processes like basic oxygen steelmaking and electric arc furnaces, impurities are purged, and alloying elements are introduced, each playing a pivotal role in sculpting steel's properties to meet the demands of its myriad applications. Here, the principles of metallurgy take center stage, as precise control over temperature, composition, and processing techniques determines the final characteristics of the steel, or whether it be the hardness of tool steel, the corrosion resistance of stainless steel, or the ductility of structural steel. But the journey of steel does not end with its creation. Rather, it is but a prelude to a saga of engineering marvels and feats of physics. Through processes like hot rolling, cold rolling, and forging, the molten metal is shaped and molded into an array of forms, each with its own unique properties and applications. Here, the principles of mechanics come into play, as forces are applied, and stresses are calculated to ensure that the steel meets the rigorous demands of its intended purpose. In the realm of structural engineering, for instance, steel beams and columns bear the weight of skyscrapers, bridges, and stadiums, their designs meticulously crafted to withstand the forces of gravity, wind, and seismic activity. Furthermore, the properties of steel can be further enhanced through heat treatment to a delicate balance of temperature, time, and quenching medium that alters its microstructure and mechanical properties. Here, the laws of thermodynamics dictate the transformation of austenite into martensite, ferrite, or pearlite, imparting strength, hardness, and toughness to the steel. By harnessing these principles, engineers can tailor steel to meet the exacting requirements of specific applications, whether it be the wear resistance of cutting tools or the fatigue strength of automotive components. The engineering and physics behind steel are a testament to the triumph of human ingenuity and the relentless pursuit of excellence. From its humble origins in the bowels of a blast furnace to its lofty perch atop the skyline of modern civilization, steel stands as a beacon of progress, a monument to the boundless potential of science and technology. In its alloyed embrace, we find strength, resilience, and the promise of a future forged in the fires of innovation. The journey of steel commences amidst the infernal blaze of the blast furnace, a crucible of unparalleled heat and chemical transformation. Within its fiery depths, a delicate dance of elements unfolds, orchestrated by the principles of metallurgy and the immutable laws of physics. Iron ore, the raw material of steelmaking, is fed into the furnace alongside limestone and coke, forming a potent triad of ingredients essential to the alchemical process. As temperatures within the furnace soar to over 1,500 degrees Celsius, the iron ore undergoes a profound metamorphosis, transitioning from solid to molten form. This molten metal, akin to liquid fire, becomes the canvas upon which the artistry of metallurgy is painted. Yet, amidst the seething cauldron of molten iron, impurities lurk, contaminating the purity of the alloy and compromising its mechanical properties. Enter limestone, the unsung hero of the steelmaking process. Acting as a flux, limestone binds with impurities such as silica, sulfur, and phosphorus, forming slag, a molten byproduct that floats atop the surface of the molten iron like a spectral veil. Through the marvels of physics, this slag is skimmed off, carrying with it the unwanted impurities and leaving behind a purified pool of molten iron, ripe for transformation. But what of carbon, the elemental soul of steel? Here, the role of coke, derived from coal, cannot be overstated. As the furnace rages on, coke undergoes a process of pyrolysis, releasing volatile compounds and leaving behind a residue rich in carbon. It is this carbon that infuses the molten iron with strength and resilience, transforming it from mere metal into the alloyed wonder that is steel. The physics behind this alchemical marriage of iron and carbon are as intricate as they are awe-inspiring. At the atomic level, iron atoms arrange themselves in a crystalline lattice, forming grains that lend steel its distinctive structure. With the addition of carbon, these grains become imbued with newfound strength, as the interstitial carbon atoms impede the movement of dislocations within the lattice, reinforcing the material against deformation. In essence, the journey of steel is a testament to the ingenuity of humankind and the boundless potential of scientific inquiry. From the fiery depths of the blast furnace to the towering edifices of modern civilization, steel stands as a monument to the indomitable spirit of progress, forged in the crucible of human endeavor and shaped by the immutable laws of physics. As the molten iron emerges from the blistering confines of the furnace, it embarks on a transformative journey guided by the principles of physics. This journey, reminiscent of a symphony, orchestrates the expulsion of impurities with precision akin to a maestro conducting an ensemble. Within the crucible of bessemerization or basic oxygen steelmaking, the molten metal encounters a meticulous purification process, where impurities such as sulfur, phosphorus, and excess carbon are coerced into separation through the alchemy of heat and chemical reactions. These unwanted elements are compelled to part ways with the molten iron, leaving behind a purer, sincere essence known as hot metal, poised for further refinement. In the sanctum of the steel mill, hot metal assumes the mantle of potentiality, awaiting the deft touch of alloying to imbue it with bespoke properties. Like a sculptor shaping clay, metallurgists carefully introduce precise amounts of carbon into the molten pool, a delicate dance dictated by the desired characteristics of the steel. This infusion of carbon, typically ranging from 0.2% to 2.1%, represents a convergence of engineering and physics, where the interplay of atomic structures and chemical bonds dictates the material's future behavior. It is a symphony of atoms, each note resonating with the promise of strength, resilience, and ductility, harmonizing to create the symphony of steel. Within the crucible, the alloying process heralds a symphony of atomic rearrangement, as carbon atoms intermingle with iron atoms to form a lattice of unparalleled complexity. This lattice, akin to a vast network of interconnected nodes, defines the material's mechanical properties, shaping its response to external forces and environmental conditions. Through the lens of physics, this lattice becomes a battleground where dislocations, tiny defects in the atomic structure, contend against the forces of deformation. The presence of carbon atoms within the lattice serves as sentinels, fortifying the material's defenses against yielding, fracture, and fatigue, forging a steel of unparalleled strength and durability. As the alloying process reaches its crescendo, the steel emerges from the crucible reborn, a testament to the marriage of engineering ingenuity and the laws of physics. It is a material of boundless potential, poised to shape the world around it with its strength, versatility, and resilience. From the soaring skyscrapers that pierce the heavens to the intricate machinery that powers our civilization, steel stands as a testament to human achievement, to a symphony of engineering and physics, echoing across the annals of history. But steel's journey does not culminate with its initial alloying. Rather, it marks the inception of a meticulous orchestration of heat treatment, shaping, and manipulation. In the crucible of the foundry, where temperatures soar to over 1,500 degrees Celsius, the molecular dance of steel begins. Picture the atoms within the steel lattice, their movements akin to a symphony conducted by the flames, aligning themselves into intricate patterns that govern the material's mechanical behavior. This choreography is not haphazard but rather governed by the laws of thermodynamics and kinetics, with each phase transformation and grain boundary migration sculpting the steel's ultimate properties. Through processes like quenching and tempering, the metallurgist assumes the role of an alchemist, fine-tuning the molecular structure of steel to imbue it with strength, toughness, and resilience. Quenching, where the heated steel is rapidly cooled in a bath of oil or water, freezes the atoms in a state of high energy, locking them into a rigid structure known as martensite. However, this newfound strength comes at a cost of brittleness. Enter tempering, a delicate balance of heat and time, where the steel is reheated to a precise temperature, allowing the martensite to transform into a more ductile and resilient structure. This interplay of heating and cooling is not merely a mechanical process but a manifestation of the intricate interplay between thermodynamics, kinetics, and material science. Moreover, the engineering behind steel extends beyond its mere manipulation in the foundry. It permeates every facet of its application, from the towering edifices of architecture to the precision instruments of industry. Consider the construction of a skyscraper, where the structural engineer must navigate the complex interplay of forces of gravity, wind, seismic activity to ensure the integrity of the steel framework. Here, the principles of structural mechanics come into play, with each beam, column, and brace meticulously designed to withstand the myriad stresses imposed upon it. In the realm of automotive engineering, steel assumes a multifaceted role, balancing the conflicting demands of strength, weight, and cost. Advanced high-strength steels, AHSS, push the boundaries of material science, offering unprecedented levels of strength and crashworthiness while maintaining a lightweight profile. Through techniques like hot stamping and tailor blanking, automotive engineers are able to sculpt steel into complex shapes with unparalleled precision, ushering in a new era of safety and performance. The engineering and physics behind steel are a testament to the boundless potential of human ingenuity and scientific inquiry. From the inferno of the blast furnace to the soaring heights of modern architecture, steel stands as a monument to the triumph of intellect over adversity. As we continue to push the boundaries of material science and engineering, let us marvel at the wonders of steel and the infinite possibilities it holds for the future of humanity. The physics behind steel's strength lies in its crystalline structure. At the atomic level, iron atoms arrange themselves in a cubic lattice, forming grains that give steel its distinct texture. The alignment of these grains, coupled with the presence of carbon atoms interspersed within, creates barriers that impede the movement of dislocations or tiny defects in the lattice, thereby reinforcing the material against deformation. At the heart of steel's formidable strength lies a mesmerizing ballet of atoms, orchestrated with precision at the atomic level. Picture, if you will, a vast expanse of crystalline lattice, where iron atoms congregate in a symphony of arrangement, forming a cubic structure that defines the very essence of steel. These grains, akin to the building blocks of a grand architectural marvel, bestow upon steel its distinctive texture and resilience. Yet, it is within this lattice that the secrets of steel's strength lie concealed, waiting to be unraveled by the keen eye of the physicist. In this intricate dance of atoms, carbon emerges as a silent protagonist, interspersing itself amongst the iron lattice in a delicate embrace. It is this union that transforms mere iron into the mighty alloy we know as steel, imbuing it with a strength far surpassing that of its elemental counterpart. But the true marvel lies in the barriers erected by these carbon atoms, acting as sentinels against the insidious march of dislocations or tiny imperfections within the lattice that threaten to unravel the very fabric of steel's structure. Dislocations, those minuscule defects that haunt the crystalline realm of materials, seek to propagate like whispers in the wind, spreading their influence and weakening the integrity of the lattice. Yet, in steel, they are met with resistance, thwarted by the formidable barricades erected by the carbon atoms. Picture these dislocations as travelers traversing a treacherous terrain, only to find their path obstructed by an impregnable fortress, their progress halted and their influence contained. It is this interplay of forces, so this delicate equilibrium between dislocation, movement and carbon barrier that imbues steel with its unparalleled strength and durability. Forged in the crucible of physics, steel emerges as a testament to the triumph of human intellect over the forces of nature. It is a material unrivaled in its versatility, finding application in realms as diverse as skyscrapers soaring towards the heavens and bridges spanning yawning chasms. Yet, the story of steel's strength is far from static. It is a narrative of perpetual evolution, driven by the ceaseless pursuit of engineering excellence. Through advanced techniques such as microalloying and thermomechanical processing, scientists and engineers push the boundaries of what is possible, unlocking new frontiers in material science and ushering in an era of unprecedented innovation. In the grand tapestry of human achievement, steel stands as a shining beacon of progress, a testament to the indomitable spirit of discovery and exploration. As we gaze upon the towering edifices of our modern world, let us not forget the silent symphony of atoms that underpins their existence, and the boundless potential that lies within the humble alloy we call steel. Moreover, the addition of alloying elements such as manganese, chromium, nickel, and molybdenum introduces further complexity to the steel matrix, enhancing its corrosion resistance, hardness, and machinability. Each element plays a distinct role in the interplay of forces within the steel, influencing its behavior under varying conditions of stress, temperature, and environment. The infusion of alloying elements like manganese, chromium, nickel, and molybdenum into the steel matrix heralds a profound transformation, elevating this humble material to new heights of performance and versatility. Consider manganese, for instance, a stalwart guardian against brittleness, weaving its way into the crystalline lattice, fortifying the steel against the ravages of stress and fatigue. Its presence alters the very fabric of the steel, imbuing it with resilience and toughness, vital qualities in the crucible of industrial applications. Chromium, on the other hand, emerges as a bulwark against corrosion, forming a protective oxide layer that shields the steel from the corrosive onslaught of oxygen and moisture. In the ceaseless battle against entropy, chromium stands as a sentinel, warding off the forces of decay and degradation, ensuring the longevity of steel structures in the face of adversity. Similarly, nickel emerges as a silent architect of strength, orchestrating the symphony of atomic bonds with finesse and precision. Its strategic placement within the steel lattice engenders a delicate balance between ductility and hardness, conferring upon the material a resilience that defies conventional wisdom. Molybdenum, with its enigmatic allure, imparts a whisper of exoticism to the steel alloy, imbuing it with a tenacity that borders on the sublime. Its atomic dance within the crystalline matrix engenders a resilience that transcends the mundane, allowing steel to traverse realms hitherto unexplored. Indeed, the alloying of steel is a delicate ballet of physics and chemistry, where each element assumes a role of paramount importance in shaping the material's properties and performance. It is a testament to the ingenuity of humanity, where the alchemy of metallurgy converges with the principles of engineering to forge a material that defies the constraints of nature. In the crucible of innovation, engineers and scientists alike harness the elemental forces of the universe to craft materials of unparalleled strength, durability, and resilience, propelling civilization ever forward on the inexorable march of progress. Moreover, the interplay of these alloying elements extends beyond mere mechanical properties, permeating every facet of steel's existence. Consider, for instance, the machinability of steel, a seemingly mundane attribute that belies its profound significance in the realm of manufacturing. Here, the addition of alloying elements assumes a transformative role, dictating the ease with which steel can be shaped, formed, and manipulated into intricate geometries. Chromium, with its penchant for hardness, bestows upon steel a rigidity that lends itself to precision machining, allowing engineers to carve intricate designs with surgical precision. Nickel, with its supple grace, imbues steel with a malleability that defies convention, enabling the fabrication of complex structures with effortless ease. In the hands of skilled artisans, steel becomes a medium for expression, a canvas upon which dreams are wrought in the fires of creativity. In essence, the addition of alloying elements to steel is a testament to the boundless potential of human endeavor, where the principles of physics and engineering converge to unlock the secrets of the universe. It is a journey fraught with challenges and triumphs, where the quest for perfection drives us ever onward in the pursuit of excellence. As we stand on the threshold of a new era, let us marvel at the wonders of steel and the infinite possibilities it holds for the future of humanity. Indeed, the engineering prowess encapsulated within the realm of steel knows no bounds. From the towering skyscrapers that pierce the heavens to the humble bridges that span yawning chasms, steel stands as a testament to human achievement and the triumph of intellect over adversity. Its versatility knows no bounds, finding application in industries as diverse as automotive, aerospace, construction, and manufacturing. The engineering prowess embodied in steel is a testament to human ingenuity, a symphony of physics and metallurgy orchestrating the creation of structures that defy gravity and stand as monuments to human achievement. Consider the towering skyscrapers that pierce the heavens, their steel skeletons bearing the weight of countless floors with grace and resilience. Behind every beam and girder lies a meticulous calculation of forces, a delicate balance of strength and flexibility engineered to withstand the relentless forces of wind, seismic activity, and the weight of the structure itself. In the realm of transportation, steel reigns supreme, powering the automotive industry with its unparalleled strength, durability, and formability. From the chassis of racing cars hurtling around the track at breakneck speeds to the robust frames of trucks traversing rugged terrain, steel serves as the backbone of modern mobility. Its ability to absorb energy during collisions, coupled with advancements in metallurgical engineering, has revolutionized vehicle safety, saving countless lives on roads around the world. In the aerospace sector, steel takes flight, pushing the boundaries of human exploration beyond the confines of Earth's atmosphere. Within the fuselage of commercial airliners, steel alloys withstand the extreme pressures and temperatures encountered during flight, ensuring the safety of passengers and crew. In the crucible of innovation, engineers continuously refine the composition and manufacturing processes of aerospace-grade steels, striving to reduce weight without compromising strength. A delicate dance of physics and materials science that enables the dream of flight to soar ever higher. Across the expanse of construction, steel bridges chasms and spans rivers, connecting communities and facilitating the flow of commerce and ideas. Behind every rivet and weld lies a deep understanding of structural mechanics, a mastery of materials that allows engineers to design bridges capable of withstanding the forces of nature and the passage of time. Whether it be the iconic spans of suspension bridges or the elegant arches of steel trusses, each structure stands as a testament to the synergy between engineering and physics, a triumph of intellect over adversity. In the realm of manufacturing, steel is the lifeblood of industry, powering the machinery and infrastructure that drive economic progress. From the assembly lines of automotive factories to the furnaces of steel mills, its versatility and strength enable the mass production of goods that shape our daily lives. Through precision engineering and advances in metallurgical science, manufacturers harness the inherent properties of steel to create products of unparalleled quality and durability, laying the foundation for a future built on innovation and progress. In the crucible of innovation, steel undergoes a perpetual metamorphosis, perpetuated by the relentless pursuit of excellence. This relentless drive stems from the fusion of engineering acumen and a deep understanding of the fundamental physics governing material behavior. Advanced techniques such as microalloying epitomize this quest for perfection, where minute additions of elements such as vanadium, niobium, and titanium impart remarkable enhancements to steel's mechanical properties. At the atomic level, These alloying elements precipitate as fine particles within the steel matrix, serving as pinning points for dislocations and hindering their movement, thereby bolstering the material's strength and toughness. Furthermore, powder metallurgy emerges as a cornerstone of modern steelmaking, revolutionizing the production process and unlocking new frontiers of possibility. In this method, finely powdered metals are compacted under high pressure and sintered at elevated temperatures, fusing them into a dense, homogeneous mass with tailored properties. This innovative approach offers unparalleled control over material composition and microstructure, enabling the creation of steel alloys with extraordinary strength-to-weight ratios and superior resistance to fatigue and wear. The physics behind powder metallurgy lie in the intricate interplay of particle size, shape, and distribution, which dictate the final properties of the sintered steel. Thermomechanical processing represents yet another milestone in the evolution of steel, harnessing the synergistic effects of temperature and mechanical deformation to refine its microstructure and enhance its performance. Through techniques such as controlled rolling, accelerated cooling, and reheating, steel undergoes a series of carefully orchestrated transformations that optimize its mechanical properties while minimizing undesirable features such as grain coarsening and phase segregation. At its core, thermomechanical processing exploits the principles of crystal plasticity, wherein the movement of dislocations within the steel lattice is guided and controlled through precise manipulation of temperature and strain rate. By judiciously engineering these parameters, metallurgists can tailor the microstructure of steel to meet the exacting demands of specific applications, whether it be in automotive components, structural frameworks, or aerospace materials. In this relentless quest for perfection, the boundaries of what is possible are continuously pushed, blurring the lines between imagination and reality. The crucible of innovation becomes a playground for daring experiments and audacious ideas, where failure is not a setback but a stepping stone towards greater discovery. Through collaboration and interdisciplinary synergy, engineers and scientists unravel the mysteries of steel, unlocking its full potential and paving the way for a future where materials defy convention and redefine the limits of possibility. In this new era of high-performance materials, steel stands as a beacon of human ingenuity, a testament to our collective resolve to conquer the unknown and shape a world limited only by the boundaries of our imagination. In conclusion, the engineering and physics behind steel represent a profound fusion of scientific inquiry and technological prowess. At its heart, steel embodies the intricate dance of atoms and the formidable forces that shape its properties. Through a symphony of metallurgical processes, from the smelting of raw materials to the refinement of its crystalline structure, steel emerges as a marvel of human ingenuity. The precise control of heat, alloy composition, and mechanical manipulation imbues steel with a vast spectrum of characteristics, from strength and durability to ductility and machinability. As we delve deeper into the physics of steel, we uncover a world governed by the principles of material science and mechanical engineering. The arrangement of atoms within the steel lattice, coupled with the presence of alloying elements, dictates its mechanical behavior under various conditions. Through techniques such as quenching and tempering, engineers can tailor the microstructure of steel to achieve specific properties, whether it be high strength for structural applications or enhanced toughness for industrial machinery. Moreover, the engineering applications of steel extend far beyond its mechanical properties. Its excellent electrical conductivity makes it indispensable in the realm of power generation and transmission, while its magnetic properties find utility in countless electronic devices and motors. The corrosion resistance of stainless steel renders it ideal for harsh environments such as marine and chemical processing, where durability is paramount. Indeed, the versatility of steel knows no bounds, finding application in virtually every facet of modern life, from the gleaming spires of skyscrapers to the intricate machinery of manufacturing plants. Steel stands as a testament to human achievement and the relentless pursuit of progress. Its ubiquity in construction, transportation, energy, and infrastructure underscores its indispensable role in shaping the world as we know it. As we stand on the precipice of a new age, the wonders of steel beckon us forward into a future brimming with possibility. Advances in materials science and manufacturing techniques promise to unlock new frontiers in steel technology, ushering in an era of lighter, stronger, and more sustainable materials. Whether it be in the quest for renewable energy, the exploration of outer space, or the development of cutting-edge technologies, steel will continue to serve as the backbone of human progress. In this ever-evolving landscape, let us marvel at the infinite possibilities that steel holds for the future of humanity. From the depths of the earth to the far reaches of space, steel stands as a testament to the indomitable spirit of innovation and the boundless potential of human endeavor. As we continue to push the boundaries of what is possible, let us draw inspiration from the enduring legacy of steel and the remarkable journey that brought us to this moment in history.